Somewhere in a small farm in South Asia, a farmer is standing in front of a mango tree that has never given him a single good fruit. He planted it from seed 7 years ago. He watered it through 2 droughts. He protected it through 3 pest seasons. And after all of that, after 7 years of patience and labor, the mangoes it produces are small, stringy, sour, and completely unsellable. His neighbor, standing right next to him, has a tree that is only 3 years old. It is loaded with large, golden, perfectly sweet mangoes, the kind that fetch triple the price at market. The difference between these 2 trees is not luck. It is not the soil. It is not the water. It is one single technique performed with a sharp blade and a steady hand that has been quietly revolutionizing fruit farming for thousands of years. It is called grafting. And once you understand what it actually does, you will never look at a fruit tree the same way again. Grafting is, at its core, the art of joining 2 different plants together so that they grow as one. It sounds simple. It sounds almost too simple to matter. But the implications of what happens when you successfully graft a fruit tree are so profound that they essentially rewrite the rules of how fruit grows, how facing trees produce, how disease is managed, and how a farmer controls the quality of every single fruit that comes off every single branch. This is not a modern agricultural trick invented in a laboratory. Grafting has been practiced for over 4,000 years, documented in ancient Chinese texts, described by Roman agricultural writers, and passed down through generations of farmers across Asia, the Mediterranean, and the Americas. But it is only in the last few decades, with our deeper understanding of plant biology, that we have truly begun to understand why it works, and just how powerful it really is. To understand grafting, you first need to understand the problem it solves. When you grow a fruit tree from seed, any fruit tree, whether it is a mango, a guava, an apple, or a citrus, you are essentially rolling a genetic dice. Every seed is a unique individual. It carries genes from both parent trees, mixed and reshuffled in ways that are almost impossible to predict. This is exactly how it works in nature. Genetic diversity is nature's strategy for survival, ensuring that some offspring can handle drought, some can handle disease, some can handle cold. But for a farmer, genetic diversity is a nightmare. It means you cannot predict what fruit your tree will produce. You might get something wonderful, or you might get something terrible. And you will not find out for years, because most fruit trees grown from seed take anywhere from 5 to 10 years before they produce their first harvest. 7 years of waiting to discover your mango tree grows sour fruit is not a hypothetical. It is a reality that has broken the finances of farmers for centuries. Grafting eliminates that uncertainty entirely. Here is how. Instead of growing a tree from seed, you take a cutting from a tree that is already known, a tree whose fruit quality, yield, and characteristics are proven and documented. That cutting is called the scion. It carries the exact genetic identity of the parent tree, not a reshuffled mix, but a perfect genetic copy. You then take a second tree, one that has been grown specifically for its root system, chosen for its vigor, its disease resistance, its ability to thrive in local soil conditions. That second tree is called the rootstock, and you join the 2 together, scion onto rootstock, in such a way that their vascular systems, the internal plumbing that carries water and nutrients through a plant, fuse, and become one. When the union heals, you have a single tree with 2 different genetic identities working in perf-CT partnership, the roots of one, the fruit-producing branches of the other. The result is a tree that combines the best qualities of both, fruits reliably within 1 to 3 years instead of 7 to 10, and produces fruit that is genetically identical to the original proven parent tree every single time. Now take this concept and apply it specifically to mango, and the picture becomes even more striking. Mango is one of the most beloved and economically valuable fruits in the world. India alone produces over 20 million tons of mango every year. Varieties like Alfonso, Deshairy, Langra, and Kesar command extraordinary prices, not just domestically, but in international export markets. The difference in price between a commercially grown, high-quality Alfonso mango and a seed-grown mango of unknown variety can be 10 to 1. Farmers who can consistently produce known, premium varieties have a product the market will pay for. Farmers who plant from seed are gambling. Grafting is what converts the gamble into a business. The most widely used grafting technique for mango is called veneer grafting, and it is worth walking through in detail because the precision of it is what makes it work. You begin with a rootstock plant that has been grown in a container or nursery bed for several months, until its stem is roughly the thickness of a pencil. You select a scion, a healthy shoot tip from a proven mango variety, that is mature enough to have hardened slightly but young enough to still be flexible. You make a shallow, downward, slicing cut into the side of the rootstock stem, creating a small pocket. You then cut the base of the scion into a matching wedge shape. The two cut surfaces are pressed together with maximum contact between the green cambium layers, the thin ring of actively dividing cells just beneath the bark. Horticulture, because it is the cambium that must fuse for the graft to take. You wrap the union tightly with grafting tape or polythene strips to hold everything in contact and keep moisture in. Then you wait. If the graft is successful, within 3 to 4 weeks, the scion will begin pushing new growth. That new growth is the signal that the vascular systems have joined, that water and nutrients are flowing freely from rootstock to scion, and that you now have a single living plant with two genetic identities working as one. Guava grafting follows a similar logic, but with its own specific character. Guava is a faster growing, more forgiving tree than mango, and it responds exceptionally well to a technique called approach grafting or inarching, a method where two plants are joined while both are still rooted, allowing them to share resources during the union process before the scion is finally separated from its original root system. This makes guava grafting particularly accessible for small farmers and home growers because the success rate is higher and the margin for error is wider. Guava rootstocks are often selected specifically for their resistance to a devastating soil pathogen called Fusarium wilt, which has destroyed guava orchards across India, Pakistan, and Southeast Asia. By grafting a high-yielding premium variety of guava onto a wilt-resistant rootstock, farmers essentially build disease resistance directly into the architecture of the tree. The fruit quality comes from the scion. The survival comes from the roots. Together, they create something neither could be alone. This relationship between scion and rootstock is more dynamic and complex than it first appears. For decades, plant scientists assumed that once the graft union healed, the two parts simply coexisted. Rootstock providing water and minerals, scion providing photosynthesis and fruit. But research over the last 20 years has revealed something far more interesting. The rootstock and scion actually communicate with each other. Proteins, RNA molecules, and hormonal signals travel across the graft union in both directions. And these signals can influence everything from how the tree grows to when it flowers to how it responds to stress. A rootstock that has been exposed to drought conditions can send chemical signals upward through the graft union that cause the scion to partially close its leaf pores and conserve water, even if the scion itself has never experienced drought. The tree acts as an integrated system, not two separate organisms stitched together, but a new organism that emerges from the union of two. This understanding has opened up extraordinary possibilities in modern horticulture. Researchers are now exploring the use of grafting, not just to combine fruit quality with root vigor, but to transfer specific stress tolerances, disease resistances, and even nutrient uptake efficiencies from one variety to another through the graft union itself. The idea that you could essentially reprogram certain characteristics of a scion by choosing the right rootstock, without any genetic modification, without any laboratory intervention, using only a blade and a piece of tape, is one of the most exciting frontiers in plant science today. But for the farmer standing in that orchard, the science matters less than the result. And the results of grafting are visible and measurable in ways that transform livelihoods. A grafted mango tree of the Alfonso variety will begin flowering within 18 months to 2 years of grafting. A seed-grown mango tree will take 6 to 8 years to reach the same point. In those missing 4 to 6 years, the farmer on the grafted orchard has already harvested 3 or 4 seasons of premium fruit. He has already recovered his investment. He's already profitable. His neighbor with the seed-grown trees is still waiting, still watering, still paying labor costs with no return. The economics of grafting are not subtle. They are the difference between a farm that survives and one that doesn't. There are, of course, challenges. Grafting requires skill. A clean, precise cut is not negotiable. Any rough surface, any gap between the cambium layers of scion and rootstock reduces the chances of a successful union. Contamination of the cut, surface with soil or moisture before the graft is wrapped can introduce pathogens that kill the union before it heals. The timing matters. Grafting during periods of active growth, when the cambium is dividing rapidly, produces far better results than grafting during dormancy or heat stress. And the aftercare is critical. The grafted plant must be kept in controlled humidity and partial shade for the first few weeks, protecting the new union from the stress of full sun and wind while it heals. These are learnable skills, but they take practice. The best grafters in commercial nurseries have performed the technique so many times that it becomes instinctive. The angle of the cut, the pressure of the wrap, the reading of the plant's condition before the blade touches the stem. In many farming communities across India, Pakistan, and Southeast Asia, professional grafters move from farm to farm during the grafting season, carrying their tools and their knowledge like a traveling trade. They are paid per successful graft, which creates a direct incentive to get it right. A skilled grafter can perform hundreds of grafts in a single day. The nursery industry that has grown around grafted fruit trees is now worth billions of dollars globally, supplying certified, variety-specific grafted plants to commercial orchards and home gardens alike. When you buy a mango sapling from a reputable nursery and it tells you it is an Alfonso or a Quesar, that certainty, that guarantee of what you are growing exists entirely because of grafting. Without grafting, the nursery could only offer you a gamble. What began as an ancient farmer's discovery, that two-cut stems pressed together and bound with cloth could fuse into a single living plant, has become the backbone of modern fruit production. Every premium mango you have ever eaten, every crisp guava from a well-managed orchard, carries in its existence the quiet testimony of a graft made somewhere, on some day, by hands that understood what a blade and a steady grip could accomplish. The farmer who learned grafting stopped gambling with his land and started making decisions. He chose his roots. He chose his fruit. He chose his future. And the tree grew exactly as he planned because, for the first time, the tree was exactly what he made it to be.